This video is about defining trigonometric functions. As always, begin by reading through the textbook and taking careful notes, but now consider some important highlights in this video. We'll begin by recalling the unit circle that we've developed in previous lessons. We started out understanding what I called special fractions of the unit circle, and then we turned those special fractions into special arcs, considering that really they're fractions of the full circumference of the circle, which is 2 pi. And then all those special arcs have terminal points, or points where they stop around the circle, and we also defined those. So the full unit circle is now displayed in this lesson. It's a great thing to review until it's confidently in your memory and able to be drawn from nothing. Because if we understand this unit circle, including all the special arcs and all the terminal points, we can do a whole lot with it. And that's where we're going today. So, considering the unit circle, let's define some things. If we let real number t be any arc length starting from standard position 1, 0. Okay, so you might recall that as we developed our special arcs and special fractions on the unit circle, they always began at this point 1, 0 on the right side of the unit circle. And beginning there, we extended positively in a counterclockwise direction. So, for example, to find an arc of length pi over 3, we would extend from the right side, the point 1, 0, up counterclockwise until we stop at length pi over 3. And then there's a terminal point there with an x and a y coordinate. All right, so those are things we've already built together on this unit circle from previous lessons, but we're going to use all those things here. So t, as defined here, a real number, is really just this arc length that we extend. So if I extend it up to pi over 3, that would mean like t equals pi over 3, the length of that arc. All right, so that's part of our definition. Now, let's keep going. Because we're starting at 1, 0 with terminal point P. So P, again, is just any of these points where the arcs stop. They're in all our special fraction places or special arcs on the unit circle. And so those points, P, have an x and a y coordinate. We've worked with these also in previous lessons. And those are what we're working with now to define these following 6 trigonometric functions. The first one is pronounced sine of t, and in this case t is the input. Remember, t is our arc length, and the sine of t is equal to y being the y coordinate of the terminal point. Okay, so we'll be using these with plenty of examples shortly. I just wanted to find them here first though. Turns out cosine of t, abbreviated cos, that's the x coordinate of the terminal point. And then the tangent of t, abbreviated tan, is the ratio of y over x, the y coordinate divided by the x coordinate for whatever the terminal point is. And of course, we're not allowed to divide by 0, so we have to say x cannot equal 0 for tangent. All right, moving on, we also have cosecant, abbreviated CSC. And so the cosecant of t is 1 over y, again y coming from the y coordinate of the terminal point, and of course we can't divide by 0, so we have to restrict y from being 0 in that case. Next we have secant of t, abbreviated SEC, and that value is 1 over x, where x again is the x coordinate of the terminal point, and of course x can't be 0 because we can't divide by 0 here. And sixthly here, cotangent of t, abbreviated COT, and this is the ratio of x over y, where x and y are the coordinates of the terminal point, and again we can't divide by 0, so y can't be 0 there. Now you'll notice that these could be arranged in pairs. They're all using the same input, which is t. Remember, t is this real number that represents the arc length, the special arc length. So let's go up here and just take a very simple example of these. If I extend an arc, and let's do this just visually to get an idea. If I extend an arc starting from the point 1, 0, up in a positive counterclockwise direction, and I'll just stop at the first place where t would be pi over 6. In that case, I would say the following. For example, the cosine of t, remember from below, cosine is the x-coordinate. So I would simply use the x-coordinate of that terminal point, which for the first terminal point is square root of 3 over 2. Or similarly, sine of t, again assuming t is pi over 6, that little arc length there to start, the sine of that arc is the y-coordinate, which in that case is 1/2. We're just getting those numbers directly from the coordinates of the terminal point there. Okay, and so on it goes, right? All of these trig functions are defined in the same way. Your input is whatever the arc is that's giving you or stopping at the terminal point, and then x or y is coming directly from the coordinates of those terminal points. And the same goes all the way around the circle for whatever function and whatever arc and whatever combination thereof we might be using, as we'll see shortly with some examples. Now let's note a couple things. First of all, these trigonometric functions are also known as circular functions. Circular functions. Some textbooks are referring to them more so as circular functions, but they're just trigonometric functions since they are defined in terms of the unit circle, as I just demonstrated above. And then secondly, note that the domains of some of these functions are restricted so that we're not dividing by 0 as demonstrated above. Now, what can be somewhat tricky or confusing at first with these trig functions is the fact that we are possibly used to using x for the domain or input value. Usually in algebra, that's the case. In trigonometry, now we're using t, and that can be a little confusing because now all of a sudden, wait, what is t? I still see an x, but where does t come from? Remember, t is the arc length, and then x is the x-coordinate of its terminal point. So there's a subtle distinction there that can be a little tricky, but once you get used to it, it's not that bad. Okay? Nonetheless, the domains of these trig functions, when we say domain, we're talking about the t values, not the x values. Okay? Because the input of the functions for these trig functions are the t values, the arc length, the special arc length. The x values are just the coordinates of where they stop, the x coordinates where they terminate. Okay, let's spend some time going through some examples because that's probably what's most helpful in seeing how these operate. Let's find the exact value. Okay, exact value means we don't want a decimal approximation. We want the actual representation of it, which might include a root symbol or something. We want the exact value of the trigonometric function at the given number. Draw the arc and mark the terminal point on the graph, which is basically everything from the unit circle we have printed above, the full labeled unit circle. All right, our first example is to find the sine of 7 pi over 6. Now, to find what this equals, we start by wondering where is 7 pi over 6 on the unit circle? Well, this is exactly why we need to know the unit circle in terms of all of its special arcs or special fractions, and then eventually also the terminal point coordinates, because that's exactly what we need and all we need to answer this question. So first of all, sine of 7 pi over 6. You may recall, or you can look back at it as often as you need to until this is clear and in your memory. 7 pi over 6 is a little bit more than 1, right? That's like 1 and 1/6. So you're starting at the same beginning point, 1, 0 on the right side, and you're extending around counterclockwise as far as that value. So 7 pi over 6 means you're going to extend all the way around beyond. Remember, half of the circle is 1 pi, and so we want 1 and 1/6, so it's the next place after that. So if we go beyond to the next place after the first half circle, which is 1 pi, we get an arc that's of length 7 pi over 6. And that's extending with a counterclockwise direction. Now, what we want for this question is the sine of that value. So that means we want to know what is the y-coordinate of that terminal point. So let's begin by just recalling what the terminal point is there completely, and then we'll pick out the coordinate we need. So again, this takes a little practice to get used to what's on that unit circle, but ideally, if you know the whole thing by heart, it's not hard to pick out exactly what this point is. It should be negative root 3 over 2, comma, negative 1/2 as the coordinates of that point. Now, the sine value of the input for the arc length 7 pi over 6, as we defined above, is the y-coordinate, which is the negative 1/2. And so we only want the y-coordinate for the sine value of this trig function. And notice in the process, drawing it actually helps because then we know, we can remember exactly where the terminal point is. And we were asked to draw the arc and the terminal point just like this. Let's move on to the next one, which says, what is the sine of negative pi over 6? All right, well, you'll recall from a previous lesson that though the negative t values or arc lengths may not show up on the standard unit circle, it simply means we're moving in the opposite direction. So a negative pi over 6 value for t means you're starting at the same place, 1, 0 on the right side, but you're going clockwise, which is the negative direction, for the first mark, just pi over 6 distance. And so that short distance down to the first mark, it's in quadrant 4, that is the t value of negative pi over 6, and the terminal point has coordinates there, which will be square root of 3 over 2 for x and negative 1/2 for y. Again, just referring to the standard arcs and terminal points on our unit circle above. So if I'm trying to find the sine of negative pi over 6, remember sine is the y-coordinate, that would simply be what we see as the y-coordinate of that terminal point, which is negative 1/2. All right, and this is all coming directly from our definitions above, where again, sine is the y-coordinate of the terminal point. And obviously the rest of these all apply as well, and we'll use them as applicable for the next examples. That's how this is all tying together. Our third example says to find the sine of 11 pi over 6. So again, we started 1, 0 on the right side. We want to extend an arc, positive 11 pi over 6. That's in a counterclockwise direction if it's positive. 11 pi over 6, that's almost 12 over 6, which would be 2. And that's all the way around the circle. So 11 pi over 6, and you may recall this from just kind of practicing with the circle, it's almost all the way around. It stops one space short of going fully around the circle. And there are coordinates of that place which are actually the same as they were in the previous example. Notice it's the same point. So if you were to consider like the stopping point where we just ended, it's the same as the stopping point where we ended in the previous example, even though the t value was different. Now it's 11 pi over 6. So we just keep reusing what's on the unit circle, which is why if we're familiar with it, really we have everything we need. So with the terminal point coordinates there being square root of 3 over 2, comma, negative 1/2, just like they were for the previous example, we want the sine of this. Well, the sine is the y value, which is negative 1/2, the same thing we got in the previous example. All right, let's move on to our next example. Example D will be the sine of negative pi over 2. Again, we'll start in standard position at 1, 0 on the right side. Negative pi over 2, remember negative is in the clockwise direction, and pi over 2 is 1/4 of the circle, as you may recall. Positive pi over 2 would be going like up through the quadrant 1, 1/4 of a circle. So negative pi over 2 means we're going the opposite direction, and we'd stop at the bottom of the circle. The terminal point there would be x coordinate 0, y coordinate negative 1, so 0, comma, negative 1. And the sine value there is the y coordinate, because sine's always the y value, which means the sine of negative pi over 2 is negative 1. Next, we have the cosine of negative pi over 2. And notice we already drew that arc, this exact same one as the previous problem. So we're going to start at 1, 0 and extend it in a negative direction, which is actually clockwise, so going downward toward the bottom. We stop there. It's the exact same terminal point that we had in the previous problem because it's the exact same arc input. But this time for the cosine of that, we want the x value. So the cosine of negative pi over 2 would be 0, the x value of that terminal point. Again, just going by the definition above, where cosine is the x value. Next, let's find cotangent of negative pi over 2. Okay, so you're starting to see how these are all related. The same input is going on here. So negative pi over 2 means we start at the point 1, 0 on the right side. We extend negative, so that's clockwise downward to the bottom. That's 1/4 of the circle is pi over 2. And the same terminal point is there, so 0, negative 1/2. 0, negative 1. And we want the cotangent. So let's go up to our definition and recall that the cotangent function is defined as x over y, where of course y can't be 0. So x over y is what we're looking for, which means in this case the x coordinate, let me write this out in two forms. X over y is the general form of it, and of course our x coordinate is 0 and our y coordinate is negative 1. So now 0 over negative 1 is actually just 0, which is our final result for cotangent of negative pi over 2. Moving on, next we'll do cosecant of negative pi over 2. Again, same beginning and ending point, same arc, same terminal coordinates, 0, negative 1. But now we want the cosecant, which if we go above should be 1 over y. And so for this one, that's 1 over negative 1, which would be ultimately negative 1. As you can see, these trig functions are defined and then computed primarily from the unit circle values. So if we know the whole unit circle and can draw this whole thing from memory, we have everything we'll need. That's something that you'll be able to do at the beginning of an exam, so you won't be given the full unit circle, but most students, and I recommend this highly, like to do a brain dump where you draw the whole thing at the beginning of the test and then you have it there. So as long as you can draw this out, and sometimes, until you get it memorized clearly, it might take drawing it out once a day or a couple times a week to make sure you've got it. Let's keep going. Next we'll do cosecant of pi over 2. Well, this time our input is positive pi over 2, which means we're starting at the point 1, 0 on the right side, and we're increasing positively, so now counterclockwise up to the top of the circle. That's where pi over 2 would be according to our special fractions. And then the coordinates, the terminal point coordinates up there would be the point 0, 1. And the cosecant, as we defined it previously, is 1 over y. So as defined above, cosecant of t is 1 over y, where y is the y coordinate of our terminal point here. Well, if it's the point 0, 1, this would mean 1 over 1, which of course is just positive 1. So the cosecant of pi over 2 is 1. Moving on, next we have the cosecant of 3 pi over 2. Well, again, according to our special fractions and our special arcs, 3 pi over 2, it's positive, so we're starting at the point 1, 0 on the right side. 3 pi over 2, that's like 3 over 2, that's 1.5 pi. That's all the way around to the bottom of the circle for this arc length of 3 pi over 2. And of course, the terminal point down there is 0, negative 1, which means we have the coordinates we might need. Cosecant is really 1 over y, and the y coordinate there is negative 1, so we're looking at 1 over negative 1, which is really just negative 1. So the cosecant of 3 pi over 2 is negative 1. Moving on, next we have the sine of 25 pi over 2. Okay, well, immediately you'll recognize that's not one of our special fractions, but we've seen this before. You can convert it into one of them. If I do a little bit of fraction work here, and note that 25 over 2 is really if you think about it, 12.5. You just kind of put that into like a mixed number. The reason that's helpful is because it can take us back to what's familiar on our unit circle. If you're looking at 12.5 pi, which is really what we're looking at here, because it is 25 pi over 2, right? Then 12.5 means, well, think about this. Every time you go around half a circle, that's 1 pi, right? So if we start on the right side at 1, 0, and if I go around the circle one full time, as we've seen, that's 2 pi, but I have a lot more to go. So there's 2 pi. If I keep going around, I'll spiral this in. Another time is 4 pi. Another time is 6 pi. Another time is 8 pi. You can kind of see what's happening here. In other words, if I go around a circle one full time, I have 2 pi. Well, that means that 12 pi would be going around the circle 6 times. So let me get a thinner marker here to do this. If I go around the circle 6 times, I'll just kind of mark it with a spiral. That's 1, 2, 3, 4, 5, 6. 6 times around the circle is 6 times 2 pi, that's 12 pi, which means we only have another half pi to go, but half pi is another just quarter circle. So actually we're going to stop, our terminal point is at the top of the circle, which is the point 0, 1. And so we can actually convert this excessively large, improper fraction of 25 pi over 2 into a more familiar looking mixed number, which tells us exactly how many times to go around the circle, given that one full time is 2 pi, and then an extra half pi takes us up to the top, terminal point 0, 1. The sign value is what we're looking for. Sign is the y-coordinate. So the sign of 25 pi over 2 must be 1. That's the y-coordinate of that terminal point. Okay, and next we're given a different scenario here. In this next example, it says the terminal point, p of x comma y form, determined by a real number t is, and then they're giving us this terminal point. It's square root of 5 over 4 for the x coordinate, and then negative square root of 11 over 4 for the y coordinate. Okay, notice that's not one of our special normal terminal points. If you go back up to the unit circle, you won't find this one on it as just one of our normal ones. That's okay though, because our goal is to find the sine, cosine, and tangent of t. Now notice we don't even know what t is, right? T is just this real number, special arc, or actually it's not one of the special arcs, it's just some arc whose terminal point is defined by this point given here, which is not one of our special ones. So we want to find the sine, cosine, and tangent of that t value, but all we have is that the terminal point is here. Well, thankfully, we know that sine of t, as defined above, sine of t is equal to the y-coordinate of our point, which is given directly to us. So all we got to do is put that in. That's negative square root of 11 over 4. That's just the y-coordinate of our point given. So they gave us the terminal point, which has the x and y coordinates, and that's really all we need for this. Moving on, so cosine of t, again, cosine is the x coordinate that was provided to us as the square root of 5 over 4. Thirdly, we want to figure out what the tangent of t is. Again, we don't know what t is, but we know its terminal point, which is all we need, because we know tangent is defined above, as we did, as y over x. And so those are the coordinates of its terminal point. We have those. That would mean for this one, negative square root of 11 over 4, that's the y value, over x, which is the square root of 5 over 4. Now, we get immediately an ugly complex fraction, a fraction within a fraction, right? And so we want to simplify this much further. Let's recall that if you're dividing by a fraction, it's the same thing as multiplying by the reciprocal. So we could rewrite this fraction as negative square root of 11 over 4, that's the numerator, times the reciprocal of the denominator. So now it's 4 over the square root of 5. And in doing it this way, if we're multiplying fractions, remember we could reduce by canceling matching values in the opposite levels. So like these 4's cancel on the top and the bottom, which leaves us with negative square root of 11 over the square root of 5. Now, as we've seen previously, and is pretty common with trig material, we also will probably rationalize this. Rationalizing means we don't want to leave a root in a denominator. And so we'll do that by multiplying the top and bottom of this by the square root of 5. You may recall this from an algebra skill in the past, and we'll do that to get a final answer of negative square root of 55 on top, that's negative the square root of 11 times square root of 5, over, on the bottom, square root of 5 times square root of 5 is just 5. And this is now what we'd call the rationalized answer, which is the likely the form you would see it in, simplified in a textbook. All right, let's keep moving with some more examples. Number 3 says find the sine of, and then it gives us this expression. It's a fraction where the numerator is tangent of t, sine of t, and yes, we can assume that those are being multiplied together if they're just written next to each other. So tan t, sine t means tan t times sine t, all over cotangent t as the denominator, if the terminal point determined by t is in quadrant 3. Okay, so notice what's going on here. We're trying to find the sine, S-I-G-N, of this expression. So S-I-G-N, that sign means positive or negative, right? Not sine as in S-I-N, the trig function. So that means we have to understand what quadrant 3 means for all these values. Let's sketch just a basic quadrant diagram to remember some key things. First of all, the quadrants start in the upper right with quadrant 1, denoted Q1. Upper left is quadrant 2. Bottom left is quadrant 3. And bottom right is quadrant 4, using Roman numerals to denote these different quadrants. So we're in quadrant 3, and we got to remember what's going on in quadrant 3. Well, all the x values are, in that case, negative, because you're to the left of the y-axis, and also all the y values are negative because we're below the x-axis. So you have to understand the orientation of the Cartesian coordinate plane, which we've been using for a while now, even in previous classes. And the x value in quadrant 3 is negative because you're left of the y-axis. The y value is negative because you're below the x-axis, which means we have what we need because we're trying to find the sine of this expression. Notice we don't know what t is, so we don't know like where the terminal point is. But if it's in quadrant 3, we know enough to get the sines, the SIGN sign of this. So the tangent, remember tangent is defined above as y over x. Well, they're both negative. So y over x for tangent would be like negative over negative, which is going to be a positive. The sine of t, that's the y value, is going to be negative, as we discussed here in our quadrant. And then down below we have cotangent. Now cotangent is x over y as we defined above, but if they're the same sign, if they're both negative, negative over negative is going to be a positive. So ultimately we're looking at a positive times a negative on top, which is a negative, over a positive on the bottom. And anytime we have negative over positive, opposite signs in a fraction, then the result will be negative. So when they say find the sign, the SIGN of this expression, negative would be what the result has to be there based on putting that all together. Moving on next, we have this. If the cosecant of t, okay, so that's one of our trig functions defined above, cosecant, is greater than 0, and the secant of t is less than 0, find the quadrant. Now we're looking for the quadrant in which the terminal point determined by t lies. Okay, so let's recall a couple things before we get into this. From above, recall that the cosecant of t, so CSC, cosecant of t, we defined that above as 1 over y. That's just from what we have written in our definitions for trig functions above. We have that. We also know that the secant, so SEC of t, that's 1 over x as defined above. And what we know is a couple things here. If the cosecant is positive and the cosecant is defined as 1 over y, that means that y must be positive, because 1 over something positive would give you a positive result. Secondly, in the same way, if the secant of t is negative, let me use a different color for this here. If the secant of t is negative, then that means x must be negative, because 1 over x is how we define secant. The only way to get that negative value is if you have 1 over something negative, so x must be negative if secant is negative. Now, we can put those two things together to determine the quadrant here. So let's draw another basic, just empty quadrant. And if y is positive, then we're talking about something in the upper half. But if x is negative, we're talking about something in the left half. And so where are both of those true? Well, that would be right in quadrant 2, which is, again, the upper left quadrant. So that's where both of these things happen. Cosecant, which is 1 over y, is positive, because y is positive there. And secant, which is 1 over x, is negative, because x is negative there. There's no other place where both of those are true, so that must be our results. And lastly, number 5 here, find the values of all 6 trigonometric functions, those are just the ones we have defined above, of t, given that secant of t is 3. Okay, so they're giving us some information. Secant of t is 3, and the terminal point is in quadrant 4. Okay, well, let's see what this actually tells us here. If the secant of t is really defined as we did above as 1 over x, and we know that the secant of t is 3, then what we can say is 1 over x equals 3. Then algebraically, if we use the reciprocal of both sides of this equation that we have now, meaning you can flip both sides over to get x over 1, or just x, equals, and then it'd be 1 over 3. So you can flip both sides of a proportion, which is what this is, two fractions that are equal, giving us x equals 1/3. If that's the case, we have what we need, because we can now use the equation that we had for the unit circle. So let's recall. The equation of the unit circle is that x squared plus y squared equals 1, which means, as we've done before, you can plug in one value to find the missing one. So if x is 1/3, then I know 1/3 squared plus y squared equals 1, which means 1/9 plus y squared equals 1. And we can solve for y here by subtracting 1/9 from both sides. That leaves us with y squared equals, on the right side we have 1 minus 1/9. Well, let's think about this. We need a common denominator, which would be 9/9. So we're really looking at 9/9 minus 1/9, which is 8/9. And then we want to find y, not y squared. So we would take the square root of both sides of this equation. And when doing that, we'd end up with y equals, we'd have to have a plus or minus in there, as reviewed before. We'd have the square root of 8 over the square root of 9. Now we can reduce those a little bit, right? 8 is really 4 times 2, so it's really 2 root 2 over the square root of 9 is 3. Okay, so reducing roots, if that seems a little fuzzy to you, that's from algebra, but you might want to pause and review that as needed or ask questions about that. But that's our simplified value for y. Now, let's recall also that in this problem, they said we're in quadrant 4. Now, why does that matter? Well, because if we're in quadrant 4, then we know the y value has to be negative. So let's just kind of remind ourselves that the given information is helpful here. Y's got to be negative if we're in quadrant 4, and that helps us get the value we need. So we can say that the sine of t, of course this is our y value, which we know must be negative given this quadrant restriction, which means sine of t is negative 2 root 2 over 3. Okay, so that's helpful because we want to find all 6 of these functions. That's one of them, that's sine. Now notice that we already were given secant, so we have a few more to find. Let's list them here. Cosine of t, we're using all 6 of our trig functions defined above. Cosine of t is the x value, but we already found that earlier as just being 1/3. So we'll say the cosine of t is 1/3. And we'll build the rest from here. So we know sine, we know cosine. We can build them from here. Tangent of t, remember tangent is y over x, or sine over cosine. We have the y, we have the x, and so we can put these together. Tangent would be the value we had for y, which is negative 2 root 2 over 3. That's our y value, over x, which is 1/3. Of course, now we have a complex fraction to reduce, so we'll flip the denominator upside down and multiply. This is really negative 2 root 2 over 3 times times 3 over 1. That's the reciprocal of that denominator getting flipped over there and to multiply by it. And then notice those 3's will cancel. So really the tangent of t is just negative, let's rewrite this. The tangent of t is negative 2 root 2. There's one. So we have sine, cosine, tangent. We got to keep going to get all 6 of these. Next we could do maybe cotangent. The order doesn't really matter that we use for these. Cotangent, you'll notice, is the reciprocal of tangent. So if we already know tangent, we can just flip that thing over and make it'd be 1 over negative 2 root 2. Of course, we'd want to rationalize this, so we could multiply by the root 2 top and bottom in order to rationalize. And when doing so, we'd end up with, notice it's going to be a negative value because we had a negative sign there. We'd have a root 2 on top, and down below we'd have 2 times root 2 times root 2. Well, think about this. Root 2 times root 2 is just 2, so that times 2 would be 4. So we get negative root 2 over 4. We rewrite this for cotangent of t. We get negative root 2 over 4. Okay, how many do we have here? 1, 2, 3, 4. And then notice above, secant was given to us, so we could just rewrite that one, but it was kind of already provided that the secant of t is 3. That was given. What does that leave? Let's see. Cosecant. So, okay, cosecant. Cosecant would be 1 over y, as we had it defined previously above. So that would be, we have the y value as negative root 2, or negative 2 root 2 over 3. So it would be the reciprocal of that, which would be 3 over, the whole thing is negative. So negative 3 over 2 root 2, which of course we could rationalize by multiplying by root 2 over root 2. And this kind of works out a little bit like the rationalizing we did above for cotangent, but this result will end up as negative 3 root 2 on top over 4. Negative 3 root 2 over 4, and that's for cosecant, so we rewrite that one. Cosecant of t equals negative 3 root 2 over 4. Okay, so bundle that up, and we have 1, 2, 3, 4, 5, 6 different trig functions that we were able to get all from the one that was provided above.